I'm pleased to introduce our young but very distinguished already speaker today, Erez Berg, who's the professor at Weizmann. I think he got his PhD about 10 years ago at Stanford. I met him, and then went to Harvard for a postdoc, and then Weizmann. He has already distinguished himself with some truly remarkable contributions, developing sign-free Monte Carlo methods in interacting fermion problems, which has been at least partly successful. It's a very hard thing. And he has worked on a very wide variety of topics and really made a pivotal contribution, especially in this field of graphene multilayers. And he distinguishes himself as a theorist from his ability and interest in trying to absorb the latest experiments, which, with mysterious results, separate out the real stuff from the chaff and to concentrate on it. And he's going to give us at least a bird's eye view of the market.
I mean a bird's eye. Bird's eye.
I don't think either Erez or Berg means bird.
Thank you very, very much, Chandra, and you all for this. I am very honored to do this colloquium here. And just following up what Chandra said, there was somebody in the program, here, commented that it's interesting that our theorists actually give experimental talks. I found it fun. Hear that theorists view the experiments, and that's part of the excitement of the field. I think that there's strong interaction between theory and a experiment, and I'll try to convey some of that in this talk. Okay, so I'll be talking about exotic superconductivity in graphene based systems. These are my collaborators on this work, and I'll highlight them as I go along. Okay, so the title of this talk is exotic superconductivity. So I'd better first talk about conventional superconductors that we actually know quite a bit about. So I'll talk about superconductivity in general, and I'll define what I mean by unconventional or exotic superconductors. And then I'll argue that we now seem to have a new place to find them in. So these unusual or exotic superconductors require electrons to interact very, very strongly with each other. And we now have, in the last few years especially, have a new toolbox to really make electrons interact in a very controlled, controllable way in 2D materials. So we'll describe that. Okay, then I'll talk about how can you get electron pairing, which leads to superconductivity from repulsive interactions, why this might be going on in these multi-layer graphene systems. And I'll talk about triplet superconductors, which is another type of exotic superconductivity, which seems to arise very naturally in these systems, and what might be special about them. Okay, so that's my outline. Please ask questions as I go along. You don't have to wait to the end. Right. So what is superconductivity? So what our field is really all about is the emergent properties of many interacting quantum particles. So we know what emergence is. Okay. So we have a collection of our liquid of very strongly interacting particles, and the resulting behavior might be very different from that of individual particles. And really, superconductivity is maybe one of the most striking examples of this phenomenon of emergence in our field. Okay. So you know that superconductivity was really discovered over 100 years ago, and even though we really understand it very well by now, I think there still is this childish excitement whenever you find a new superconductor, and it still fascinates us. Nevertheless, Okay, so you know the basic phenomena. You take many materials, metals. If for the first one to be discovered was mercury, and you cool it down to very low temperatures. Okay, so this is degrees Kelvin, and you measure the resistance of this material, electrical resistance. And, there's a phase transition where the resistance slowly drops to zero. This zero is really zero to the extent you can measure. Okay, so this is one of the defining properties. Electrical current can flow through a superconductor with no resistance whatsoever. Another striking property is the so-called Meissner effect. Okay, below TC, this material expels magnetic field in its ground state. Okay, so these are the maybe strongest defining experimental properties of a superconductor. And theoretically, a good way to think about a superconductivity. There are some caveats, but a good cartoon way to think about the superconductor as a Bose condensate of bound pairs of electrons. Okay, we know that the electron is a fermion; it cannot condense, cannot Bose condense. But once electrons form these Cooper pairs or bound pairs, these typically spin singlet Cooper pairs, then these pairs of electrons can condense. More technical term, this operator creates a pair of electrons, one with spin up and one with spin down, forming a singlet pair. This operator gets a non-zero vacuum expectation value. This symmetry breaking basically is what gives rise to superconductivity. We know that even this picture is a little bit simplified. This is really a Anderson-Higgs mechanism. So these electrons are charged, but this is always a good way to start thinking about this phenomenon. Okay, so what do I mean by conventional superconductors? So this is the type of superconductivity that occurs in most metals that we know are superconducting. And of course, the basic question that people have struggled with in the beginning, in the half of the last century, is what actually makes electrons bind to each other. Okay. So the picture that to form a superconductor, the electrons first have to bind into these Cooper pairs. Of course, two electrons repel each other very, very strongly. What leads to this binding of electrons to form a superconductor? And this theory, luckily, is extremely well developed. We add that in quite a bit of detail. The basic mechanism is attractive interactions between electrons that are mediated by lattice vibrations or phonons. Okay, so these electrons in the metal are flowing on the background of the positively charged ions, and the vibrations of this ion lattice give rise to an effective attraction between electrons. Okay, so that's part of the answer. Of course, that's not that cannot be the entire answer because the electrons still repel each other very, very strongly. It's actually important that these phonons or lattice vibrations are very, very slow compared to the electrons, just because the ion mass is so much heavier than the electron mass. So these induced attractive attractions are what we call retarded. Okay, they're retarded in time, and I won't go into details, but this is the key for this relatively weak attraction to beat the Coulomb repulsion between electrons and give rise to binding of Cooper pairs. Another important part to keep in mind in the story is that, as you know, if I have two particles in three spatial dimensions in free space that attract each other very, very weakly, they would not actually form a bound state. The attractive interaction would have to exceed some critical strength. Okay. And whereas superconductivity, strikingly, it can occur even if the attraction is arbitrarily weak. And how can that be? That's because the pairing of electrons in a superconductor is not a two-particle property. It's a collective property. It's actually crucial that these electrons are not living in free space and vacuum. They're actually feeling the background of all the other electrons, most importantly through the Pauli principle. Okay. So this is a picture of what we call the Fermi surface, momentum space. We have two extra electrons on top of the free surface. And it turns out that even an arbitrarily weak attraction between these two extra electrons, is what Cooper taught us, can lead to formation of a Cooper pair. Okay. So that's the basic theory in a nutshell of conventional superconductors. And I have to say, during my career, I think this theory, even though it has been well known, has actually developed even further. So now we can do things that were considered impossible when I started my PhD. We can actually calculate it quantitatively and predict new superconductors. And this kind of program has really triumphed the last several years. Okay, so people have predicted this material, okay, so hydrogen-3 sulfur, will actually become a crystal and a superconductor at the pressure of a few millions of atmospheres. And most strikingly, the TC is actually higher than what of any known material before this prediction, and this was actually discovered in 2015. And this program actually continues. Okay, so people are predicting more and more extremely high temperature superconductors. We're actually starting to approach room temperature. It was a long-term dream of our field to find room temperature superconductors. There actually have been reports of these hydrogen-rich materials that approach or even exceed room temperature, even though they've not been repeated yet. But unfortunately, as you see, it's approaching room temperature, but the pressures are very, very far from ambient conditions. These are a billion times the atmospheric pressure. You have to have a very special device called a diamond anvil cell to reach these pressures. So what we learned here is that we've been praying and hoping for a room temperature superconductor. We had to be a little bit careful in what we wish for. We should have asked for an ambient conditions superconductor, not a room temperature superconductor. This is what we have at the moment, but I think this program is very, very promising. Okay, so these are conventional superconductors. We really understand them very well. Yes.
Promising because they can get superconductivity. In their indications, you could do it at lower pressures.
Yeah, I think that's the main challenge right now.
But I mean, are there indications that that's possible? That's been the whole people without the high pressure.
Looking for, and yeah.
So
The claim is, can you have the same sort of hydrogen-based material in a matrix that can allow the hydrogen to be in the right conditions, but in lower pressure? All right, so these are conventional superconductors. What do I mean by unconventional or exotic superconductors? So these would be materials where the pairing mechanism is really qualitatively different. So what I'll discuss in the rest of the talk are systems where the pairing mechanism is what we call all electronic, which means that the pairing actually originates directly from the Coulomb interactions. The phonons are there. They might be contributing, but in some sense, they're not essential. So it's not easy to do in the lab, but we imagine that if we could somehow freeze the ions in their position, superconductivity would not go away. It would not even change qualitatively. And I'll discuss how can that be. That sounds very counterintuitive at first sight. Okay, how can a repulsive interaction between electrons lead to binding of pairs of electrons? The consequence of this is that the Cooper pair wave function, okay, so you have a wave function of a pair of electrons. The wave function is a function of the relative coordinate. Typically, due to this mechanism, it's not a simple S wave. It's not an S wave wave function. It has a different symmetry. And this is a sharp distinction, symmetry distinction. And in fact, so this would what an S wave, a wave function of the relative coordinate of the two electrons might look like. This is E wave, and so on. In fact, one of the big triumphs of our field was the prediction and discovery of the pairing symmetry of the so-called cuprate high temperature superconductors, which is actually D wave. And this is something that you simply cannot get out of the conventional electron phonon mechanism. This was really a big advance maybe 30 years ago. And correspondingly, due to the Pauli principle, once you have a non-S wave relative symmetry of the Cooper pair, spin doesn't have to be zero. It doesn't have to be spin singlet. In fact, if it's odd angular momentum, it would be spin triplet. And I'll be talking about that as well. Now, most of the superconductors we know of are of the conventional type or the electron phonon type. Okay, but we believe that this mechanism is at work in many so-called strongly correlated materials. These are materials where electron-electron interactions are particularly strong, and these tend to have very complex phase diagrams as a result of the same strong electron-electron interactions, superconductivity is only one contender. There are many competing phases.
So yes, if it is spin one, when condense is directional, then
Absolutely, and I'll discuss that. So the Cooper pair has this extra degree of freedom. Okay, of the spin. Yeah. Okay, so just to flash a few materials. Okay, so this is a so-called strongly correlated materials. Okay, this is a heavy fermion material, an organic superconductor, a cuprate superconductor, and an iron-based superconductor. Okay, so these are the crystal structures, totally different chemically, totally different crystal structures. You see the phase diagram. Sometimes I'm plotting the phase diagram as a function of pressure and temperature, sometimes as a function of material composition and temperature. But nevertheless, you see the striking similarity in the overall shapes of these phase diagrams. You always get superconductivity in some range of parameters next to some other non-superconducting but symmetry broken phase. It may be a competing phase, maybe its mechanism is related to that of superconductivity, but it's always some kind of magnetically ordered state. And our understanding is that this magnetically ordered state is coming basically from the same electron-electron interactions. Then it's either competes or cooperates with superconductivity. But this is what the type of phase diagram we would expect for such unconventional superconductors. All right. So, the traditional way to look for these systems would be to hope that nature would be kind and just look at different materials with different quantum chemistry. Now we have this new strategy. You can actually design these materials in a remarkable level of control. Okay, the name of the game, we want interactions between electrons to be important. Okay. So what we want is a system. We really realize sort of, if you like, quantum mechanics on a massive scale. Okay, so we learned about quantum mechanics of an electron in a hydrogen atom. We have a massive number of electrons, all quantum mechanical, or all showing interference effects, but at the same time interacting with each other. Now, electrons, typically in metals, electrons are too light. Okay, so basically the interaction effects are not strong enough to modify the properties of the system in a qualitative way. Basically, you can think about it like this: electrons are just zipping past each other too fast to really kill each other strongly enough. Okay. So what we need to do is to somehow slow them down. Okay, so to make these types of effects, quantum mechanics, or if you like, the zero-point motion of electrons and the interaction effects on the same footing, you really need to slow down the electrons, which means get narrow energy bands. Okay, so that the speed in which electrons are moving is the group velocity that's related to the bandwidth of the electrons. Now, to do that, one way is to look for the right quantum chemistry, to look for materials that have a large angular momentum shells. They tend to form narrow bands. The other way is this new physics that we learn how to play using 2D materials. That's what I want to discuss next. Okay, so the material of choice for this talk would be graphene, even though you can do it with other materials as well. Okay, so we know graphene, that's this monoatomic sheet of carbon atoms forming this honeycomb lattice. And the dispersion of that is basically mimicking the Dirac equation. The electrons in graphene have a linear energy dispersion, and that's beautiful. That has many interesting properties. But the electrons, the speed, the Dirac speed of these electrons is very, very fast. Okay, so the system is very interesting. It's not very useful from the point of view of exploring a correlated electron physics. So how do we slow down the electrons in graphene? One trick that was proposed maybe a decade ago and really exploded in the last few years is taking two layers of graphene and twisting them relative to each other. Okay, so this is twisted bilayer graphene that you actually, some of you heard from Elias Dani's talk last week. Okay, so when you do this, when you place two materials on top of each other with a twist angle, you form a new lattice, which is a beading pattern between the two lattices due to the twist angle, and you form a new crystal, a new artificial crystal, the controlled lattice parameter, and a new band structure. It turns out quite strikingly, if you twist these just by the right amount, by an angle of 1 degree, you form extremely narrow energy bands. When you put electrons in these energy bands, electrons are very slow, so they interact extremely strongly. There's actually a lot of fascinating physics that emerges out of here. Electrons behave like insulators, where they should have been metals by the conventional theory, and also superconductivity emerges here. Very, very naturally, it turns out. We'll actually talk about the different trick, not twist. I'll also have multiple layers of graphene, the same material. Rather than twisting, I'll play with the stacking degree of freedom. Okay, so you can stack these things in different ways relative to each other. And because these layers are coupled, the electronic structure depends very, very sensitively on the stacking. Okay. So if you think about E, for instance, honeycomb lattices, you can stack them in these three distinct geometries relative to each other. And in the so-called AAA stacking, where all the atoms are aligned, you get that the electronic dispersion at low energy is linear. And it's the so-called Bernal or ABA stacking quadratic at low energy. You have actually two bands. One is linear and the other one is quadratic. And in the ABC stacking, it's cubic. Okay, so this is in a simple model, but it's actually factors in the actual dispersion pretty well. And the cubic dispersion means that close to zero energy, the dispersion is actually very, very flat. The electrons are very slow. And if you tune the density of electrons just right, close to this point, you actually get the interaction effects will be very, very enhanced.
Are these stacks only up to 3, or do they continue beyond?
It continues. It turns out that it's rhombohedral stacking. You can continue. You can do A, B, C, A, or any number of layers. And in the simplest model, you're just to get k to the power n. And now there are effects that are beyond the simplest model that would split this a little bit apart. Okay, this is not actually to the n down to the lowest energies, but you do get a very, very flat dispersion. Okay, now
the limit of graphite, but it just
so right. So what happens in the limit of there's rhombohedral graphite, which you just continue, and it does become more and more flat. But these states live at the surfaces of the graphite. Okay, so these are really surface states. In the trilayer, the surfaces are close. You can't really talk about the surface state. Now, let me also mention, okay, I'm treating this static degree of freedom as if it's completely it's completely our choice. Of course, there's only one of these structures, which is the ground state of 3 layers of graphene, and that's this one. Okay. That's Berglas is stacked graphene. That's the lowest energy state. But the other ones are metastable states. Okay, you can create them in the lab. It's challenging, but people have been able to do this. And electronically, it turns out that the natural one is not the most interesting one. As you might guess, for 3 layers of graphene, most interesting one is the rhombohedral one that has the flattest dispersion in close to zero energy.
Graphite Bernal?
Yes. Graphite is just continue stacking it this way.
But I see a symbol parallel there. So the electrons move mostly along the layers. So
yeah. So you see these right. So this is a momentum in the plane. Now see here multiple bands. These multiple bands come from the different layers of graphene, hybridized with each other. They also mentioned something about this, something related to that. Okay, where do these flat bands come from? Okay, so how do we start from this extremely dispersive Dirac cone of electrons, and we couple different graphene sheets together, and we get these extremely flat dispersions. So the nice thing is that this is all actually interference effects. Okay, this is destructive interference. We arrange the coupling between the layers so that there are states that, due to destructive interference, can move. Okay? This is where all of these flat bands are actually coming from. And we really learned how to do this, both in theory some decade ago and experimentally in the last few years. All right. So now I'm actually going to talk about superconductivity and trilayer rhombohedral graphene. The work done with Berg, who's a postdoc in Vienna. Elias was my former postdoc at Weizmann, Maxim from Vienna as well. Okay. There's a parallel work I won't talk about with the Berkeley group. It takes a different approach but finds similar results. we're particularly indebted to Andrea Young from Santa Barbara discussing his data with us. And this actually cited quite a bit of excitement in our field. There have been several theoretical works on this experiment. People, some of them are actually here. Okay, so this is again rhombohedral trilayer graphene. These 3 layers of graphene stacked in this ABC way. And it turns out that the very useful knob to enhance, to make the energy bands even flatter in the system is a perpendicular displacement field. So you can apply basically an electric field perpendicular to the system. You start from these very, very narrow dispersions close to a low energy. You see here that it's not quite k cubed. This is from smaller terms in the Hamiltonian that I didn't discuss. But when you apply a displacement field, it actually opens a gap at small energies, and you get very, very flat dispersions both in the bottom of this band and the top of this band. This is what density of states as a function of density looks like on the whole side, this side of the dispersion. You see here how the Fermi surface evolves, having 3 little pockets, having a annular shape, having a connected single Fermi surface. Okay, so now what the natural question is, there is this very high density of states, or very narrow, narrow dispersion in some range of momenta. If you place the Fermi level down here or up here, okay, and you can control that in the experiment, that's just controlled by the density, overall density of electrons. Okay, so that's totally controllable. You can put the density of electrons here and ask, what does the system do? Okay, what we expect is that interactions between electrons are extremely strong, and the system will become unstable. This is actually what happens. This is an experiment by Andrea Young's group. He's mapping here the phase diagram of the system and function of density of either electrons or holes, okay, positive or negative, and displacement field, varying the electron dispersion. And he's measuring basically the electronic compressibility of the system. It doesn't matter exactly how he does that, but the important thing is that as a function of density and a displacement field, you see these very, very sharp features. It turns out that what these features are these transitions between different electronic states in phases, where the system spontaneously breaks symmetry between the spins, spin up and spin down. This is a graphene system, so there's also a valley degree of freedom in addition to spin. And that symmetry between valley, what we call valley K and valley K prime, is also spontaneously broken. Okay, so what's shown here is the degeneracies of the Fermi surfaces. If you didn't have any symmetry breaking, every Fermi surface should be 4-fold degenerate because of 2 spins and 2 valleys. And you get these different phases where that symmetry is excessively broken. That's a phenomenon. It seems similar to what we believe is also going on in twisted bilayer graphene. And more recently, these phases are all metallic. Okay, the electrons can flow freely. And it turns out that if they looked much more carefully, they found that there's also superconductivity in this diagram. So some of these metallic phases, you cool them down enough, actually become superconducting. And this is basically the same phase diagram on the whole side. The color is different here. The quantity that's measured is different. This is the electrical resistance. It actually goes to 0. These 2 light strips here. Okay. So two distinct superconducting phases called SC1 and SC2. This is just a resistance as a function of density, and you see it going to 0 at low temperature. The TCs are quite low, 0.1 degree Kelvin or even less. But strikingly, you can actually study the spin state of the Cooper pair by applying them a magnetic field. And from that, they deduced that SC1 phase most probably is a spin singlet, like in a conventional superconductor, but SC2 is a spin triplet superconductor. Okay, so 2 electrons in the Cooper pair actually form a spin 1, not a spin 0. That's already very unusual. Okay, so how much time do I have?
About 20 minutes. 20 minutes.
20 minutes. Perfect. Okay. So, what I'd like to convince you and the rest of the stock that these superconductors are likely, at least, to be what I called unconventional superconductors. They're a pairing mechanism, not the usual electron-phonon pairing mechanism, and they're for sure SC2, not a totally conventional superconductor. It's a triplet superconductor, and that's by definition. By the way, I define an exotic superconductor. That is exotic, and I'll discuss a little bit what might be special about that type of superconductor. Okay, so as condensed matter physicists, what we'd like to know is what kind of superconductivity happens here. There's already a hint here. Okay, so I've shown you before these different phase diagrams of different correlated materials. Unconventional superconductivity tends to appear right at the boundary of some other competing phases, typically magnetic phase. This is exactly what happens both in SC1 and SC2. They live right at the border in different phases with different broken and valley symmetry. Okay, so this is already a hint. That, of course, is not enough. Okay, so we'd like to know what is the mechanism of superconductivity and what's the nature of superconductivity in this material. Okay, and there's an argument which I really appreciate. Actually, I think it's an argument not to be taken lightly, which is basically promoted in this paper. And I won't talk about the details, but the gist of the argument is 99.7% of the superconductors in the universe are totally conventional, okay, phonon mediated. Find a new superconductor, it's very likely to be one of those. Okay, so it's basically a conventional phonon mediated superconductor unless proven otherwise. Okay, that's really not a stupid argument. Now, I'd like to tell you why I think this might not be applicable here. Okay. So, luckily, the mechanism of phonon-mediated superconductivity is so well understood that we can try to disprove it. Okay. So if it is electron-phonon-mediated superconductivity, we should be able to calculate a lot of things and compare them to the experiment. And in particular, the same electron-phonon coupling that leads to superconductivity, they raise the temperature, actually also scatter the electrons very strongly. Okay? So if it's strong enough to lead to superconductivity, the scattering of electrons in the metallic state should also be strong. And we know that that should lead to a resistance, electrical resistance in a normal state that goes linearly with temperature. Above a certain characteristic temperature of the phonons, we can estimate in the system should be around 10 Kelvin. And this is what the experiment shows. This is in one of these superconducting phases. This is the resistance as a function of temperature. You see here the superconducting transition. But above the superconducting transition, it really looks nothing like that. It's to zeroth order temperature independent, and if anything, it actually goes a little bit down, raising temperature.
Yes, this statement true even in your after Van Hook singularity?
Yes. Yeah. So the details might be different. Okay, it might be here. But yeah. But it's roughly true. Now, notice that this goes only one way, right? I mean, if we saw this, this doesn't mean it's an unconventional superconductor. Right. But if we don't see it at all, okay, that's a problem.
Why should move some to the sun? They knew this, right?
Yeah, so I mean, right. So we thought, how can we tell? We told our little friends, how about the resistance as a function of temperature? And then they found this, and we said, aha. Okay.
I like the direction you're going, but we know very dirty metals in which the resistance looks.
Yeah. So this is an important point. This is an extremely clean system. Okay. The electronic mean free path at low temperature microns. Yeah. This is actually also important because if it was very dirty, it would be very hard to get it. Okay, and there's another puzzle which I won't go into the details of. It's more theoretical than this. And that's related to the fact that we get these two superconducting states. One is a spin singlet, and the other one is a spin triplet. That turns out to be hard to square with the conventional electron phonon mechanism. But I won't go into the details of that. Okay, so we need to consider something else, or at least that's what we believe. And there is an alternative in the theoretical literature. Okay, so this is a so-called new mechanism of superconductivity, is what was new when it was discovered. And this is the idea that you can get electrons to pair just starting from bare repulsive Coulomb interactions without the lattice being involved. And that's very, very counterintuitive. We first encountered it. And how does that work? Well, the only way it can work, of course, is because the pairing is a collective phenomenon. So because of the fact that the electrons that pair don't actually live in free space, otherwise they would never be able to bind, they really are binding on the background of this electron liquid, which is all the other electrons. And therefore, the effective interaction between two electrons close to the Fermi surface is not the bare Coulomb interaction, the 1 over R, function of space. It's a screen Coulomb interaction, which is screened by all the other electrons. And this is the calculated screened electron interaction, effective interaction, on the background of other electrons forming a Fermi surface, which has this angular shape. No, is the right shape of the Fermi surface for trilayer graphene, for the normal state of trilayer graphene. And the striking thing is that you see that the effective screen interaction has these wiggles. If you Fourier transform this effective interactions, which see all sorts of characteristic wave vectors of the underlying Fermi surface. Basically, if you put a charge in this liquid of electrons, it responds, it tries to screen, and it overscreens. This is basically this phenomenon. You see that this interaction actually goes negative. It means attractive. And if the region where it's attractive is just right, you can actually get this effective interaction to pairing electrons. Yes.
Isn't this attraction because it's essentially electron and holes and not? I mean, so
yeah. So the Coulomb, even the bare Coulomb interaction would be attractive for electrons and holes. Here, I'm more ambitious. I want an attraction between electron and electron. You can say it's one electron creating any particle hole pairs. These attract the other electron.
I think the first point is that the epsilon dp, the relation between the velocity and momentum are opposite for the two.
right.
Yes, yeah. So that's true. The carriers are hole-like on one Fermi surface and electron-like on the other.
Right.
But I still am pairing electrons. They have the same charge.
Be pairing on the same Fermi surface.
The red is red, the red is blue.
No, the pairing is red with red.
That's the question.
This is zero frequency.
This is the effective attraction at zero frequency. Yeah.
But yet this is very rare as a mechanism of superconductivity.
This is a very rare mechanism of superconductivity. You have to have just the right conditions to have this. Let me also mention this in this context that turns out that for this calculation that I'm doing, the fact that I have this particular shape of Fermi surface actually is crucial. So if I did the same thing just with a single Fermi surface, it just won't work. Okay, so you would get some superconductivity, but it would be too weak.
If I put in a defect into the system, you need to say that at a certain distance I should see a ring of electrons.
Yeah. So this is
Okay.
exactly.
This.
All right.
So the long distance gap is a small number.
Yes. Yeah. The scale is tens of nanometers. Yeah. Many lattice coefficients.
Yes.
Okay. So show you the details. We've done the calculation. What you get as a function of the hole density, you get that at very high hole density, where the Fermi surface is just a single warped circle, you get nothing. This is basically the log of TC. Okay. But then beyond a certain density, you get this bump in TC. Then it rises, this very sharp peak, the Coulomb singularity, where the Fermi surface reconnects. But the interesting thing is that over most of this density range, the pairing symmetry is P wave. It's P wave like, not S wave. And moreover, if you have P wave, you have two degenerate pairing states, Px and Py, and they have to decide how to combine. They turn out to combine in this chiral combination, delta x by delta y. That means that the Cooper pair actually breaks time versus symmetry. This means that the Cooper pair is actually spinning spontaneously. So this superconductor is actually behaving in some way like a magnet. Every Cooper pair has a magnetic moment. This is a very fascinating type of superconductivity, which is believed to occur in a few other systems. If this is the case here, it should actually have consequences. For instance, boundaries of my system should actually carry spontaneous current. Once you cool below superconducting transitions temperature, there should be a spontaneous current. And again, I won't go into the details.
I'm having trouble parsing what you just said, which seemed to indicate it exists in other systems that only has consequences in this one, or it would have the same consequences.
Oh, it's the same consequences here. Yeah. So, there are several really good candidates in some material for this phenomenon.
Effectively, how many copies of T plus IP there is in here?
Yeah. Right. So I've been a little bit quick on this. 2 spins, 2 valleys. Okay. The order parameter, if you look at the function of momentum in one valley, it looks like plus IP. But the pairing is always inter-valley. It actually pairs with the other valley. And that's why it's a little bit confusing when you first got it. The symmetry is not really necessarily wave. Could be wave. Okay, the spin state of the Cooper pair can actually be either triplet or singlet because of the fact that
Okay. An experimental fact, the time reverse of symmetry is being broken by the superconducting state.
No, that's not the experiment. It's a bit. Yes.
In helium-3, also you have similar triplet pairing and T plus IP. But here there is, unlike helium-3, here you have valleys.
Exactly.
Exactly.
Yes.
So what are some differences with helium-3?
Yeah. So right. The phase that you get here is topologically different from the phase that you get in helium-3. That's one difference. The other difference is because of the fact that you have the valleys, the state can actually be either singlet or triplet. And what we believe is happening is that in one of these 2 superconducting phases that was found, it decides to be singlet, and the other one it decides to be triplet. No difference. It's not the same triplet. It's not the same symmetry of the order parameter, but of course it's related. Okay. So and I'll mention if you will.
If it's very singlet, if it's in singlet, it's also very triplet, and other way around.
I see that there are many experts asking questions. Can we hold them off?
Right, and I'll just say very briefly, I won't go into details, but I'll argue that this pairing state actually resolves the experimental puzzles I've encountered before. You try to explain everything in terms of conventional mechanism. Okay, so in the last minutes, I'd like to zoom out a little bit and talk about spin triplet superconductors more generally. Okay, this seems to be realized in this particular system, but more generally, what is actually special about superconductors and what might be measured as a result. This is work done with my former postdoc, Eyal, with Mark Widner, who's now in Seattle. Okay, so triplet superconductivity seems to be established pretty well in this system. Also in other systems, graphene-based, also in twisted trilayer and layers, 5 layers, they all seem to have triplet superconductivity. And I'd like to say a few words about that. Actually, finding a triplet superconductor in solid state is actually sort of a long-term goal of our field. Know if a neutral superfluid, you take helium-3 atoms, they're fermionic atoms, so they form a Fermi C, just like electrons, but they're neutral. And we know that Fermi liquid of neutral atoms can become a superfluid. And that superfluid is spin triplet. The nuclear spins of the helium atoms are actually spin 1. And we've been struggling to actually find solid state systems that do the same thing. There are quite a few candidates, but it's very rare. Again, we think we understand why it's so rare, why most superconductors in the world form spin singlet. That's because to get spin triplet, you really have to get a very, very special combination of factors. You need very strong correlations between electrons, very strong interactions. It's good to have a nearby or even coexisting ferromagnetic state. And the system needs to be extremely clean. Okay, you must have a very, very good crystal with very low density of defects. Defects will destroy this type of superconductivity, whereas they won't destroy a singlet superconductor, this wave. Now, it turns out that in these graphene-based systems, all of these conditions are actually met. So in some sense, this is an ideal system to look for triplet superconductivity. You know the electronic correlations are extremely strong. You know there are many, many nearby ferromagnetic phases, and these systems are extremely clean because graphene is so clean. And I mentioned that triplet superconductivity seems to occur not just in this trilayer rhombohedral graphene, also in twisted multilayer graphenes, here 4 or 5 layers. In addition to that, graphene is a very light element, which means that it has very, very weak spin-orbit coupling. The spin is almost independent of the orbital degree of freedom, which means that in this superconductor, as was mentioned before, we have a new degree of freedom, which is the direction of polarization of the spin of the Cooper pair. The question is, that intertwine with the superconducting degree of freedom in an interesting way. Okay, and I'll just flash argument. Okay, what's the order parameter of a spin polarized triplet superconductor? Okay, so it's a particular type of triplet superconductor that's occurring in this graphene system. Okay, so if you have a triplet, as you all know, yeah, I can have a triplet which means total spin of the pair is equal to 1, but I still need to specify whether SZ is 1 or 0 or -1. Okay, this is a fully spin polarized superconductor, which means that the total spin along some quantization axis is actually 1. Okay, so the order parameter is just like a spinner of spin 1. It has a direction, say +z, and it has a phase, because the superconducting order parameter is always a complex order parameter. And you can ask, what's the order parameter space? What do I need to specify the state of such a superconductor? And clearly, I need to specify a direction and a phase. And it turns out that this direction and the phase combine into basically a rotation matrix. Okay, a matrix in SO3. Okay, it's an axis and an angle. It's like a rotation. Okay, for the experts, to specify the state of a D-wave superconductor, you can specify the so-called D vector, which is a complicity vector. This type of state is characterized by the real and the imaginary parts of the D vector being perpendicular to each other, and the direction of the magnetization is a cross product, so perpendicular to both. Okay, so that if you didn't get that, that doesn't matter. In SO3 matrix, I can specify it by a triad of vectors, which are virtually orthogonal and so at every point in space, my superconductor is characterized by this triad. Okay. This triad, the ground state would be uniform, but if I have thermal fluctuations, for instance, it would fluctuate from point to point. And as we know, this in particular means that in 2 spatial dimensions, because you cannot break a continuous symmetry, there actually should be no finite temperature transition at all. But let's imagine, so Tc is 0, the superconductor can only exist in the ground state, but I'm going to ignore this fact now. Okay, I'm just going to assume that at low enough temperature, my system is big but finite. The correlation length of the superconductor is much bigger than the system. It behaves as if it's a superconductor. It turns out that there's still something special about this type of order parameter that I'd like to point out. Okay, so in a conventional superconductor, the order parameter space is the phase. Order parameter is a complex number, and that means that the order parameter space is U1. That has interesting consequences. The topological defects of such a superconductor are so-called vortices and anti-vortices, and that has some dramatic consequences. We know that leads to quantization, the existence of persistent currents, and so on. That's all related to the fact that these defects are characterized by the integer number. A complex phase go along a closed path in real space, can wind any integer number of times. And it turns out that in a fully spin polarized triplet superconductor, where the order parameter space is SO3, these are different. The topological defect is characterized by a Z2 index. So, there are no vortices and anti-vortices, they're only vortices. Two vortices can always destroy each other, always annihilate each other. Okay, so this is related to this mathematical fact of a homotopy group, pi1 of XO3 is equal to Z2. there's a very nice way to illustrate this using a build. If you haven't seen that, I highly recommend it. This is called the Dirac build trick. Okay, what you do is the following. I practiced. I decided I'm not proficient enough. I won't demonstrate it here. But if you take a build, fix the edges, now two twists. That just by moving the ends in space, you can actually unwind the two twists. This is what it looks like. And a nice demonstration. And this is related to this mathematical fact. So yeah, okay. So what this means in practice is that in such a superconductor, if the superconducting phase winds twice, okay, by 4 pi, it can actually be unwound without creating any topological defect by creating a spin texture. Okay. That actually has some interesting physical consequences. Asa, who's here, who actually stimulated me to think about this. Okay, this would lead to an unusual AC Josephson effect. So in the usual superconductivity, there's the AC Josephson effect. If you apply a voltage superconducting junction, the current actually oscillates with a universal frequency, which depends only on the voltage. Here, because of this Z2, whenever the superconducting phase winds twice, you can unwind it. That would lead to a double period of the Josephson effect. Some other interesting consequences. The critical current of such a superconductor be mesoscopic, depend on system size. If you apply a magnetic field, it would become finite. Okay, because the plane magnetic field is the Weizmann effect in the direction of magnetization, cause this to be a real robust superconductor. So that's it. I'm basically done. Okay. So graphene seems to be a perfect platform for exotic superconductivity of various kinds. We're sure there's unit superconductivity. Maybe there's also chiral superconductivity as well. Finish.
Questions first from non-experts, non-conventional people. There are lots here. Yeah, please.
So are there any clear applications or ways in which exotic superconductors are qualitatively different from conventional superconductors in terms of things you might do with them?
Yeah, so right. So none that were discovered so far, except in one regard, which is that you know the reason why the cuprate superconductors got so much attention is, of course, because the TC was so high.
So the TC,
and they lost their crown as the highest temperature superconductor, but at ambient pressure, they're still by far the highest now. So the promise is that unconventional superconductivity is a way to get to higher.
so basically you're pushing TC higher. Okay.
Any other non-experts? Questions, please.
One of the, issues pointed out very quickly with the cuprates was that, they didn't necessarily have the ability to handle as much current.
That's not true anymore.
I was careful to say one of the issues pointed out early, so thank you for the unnecessary clarification. What's the feeling about these in that regard?
These are, yeah, so I haven't mentioned this. The ability of a superconductor to carry current depends on many factors, but the crucial factor is just how many electrons are there, the density of electrons. Here it's extremely small. In fact, these are the lowest density superconductors you know of. So these are definitely not practical.
I have a non-expert question.
One of the experts.
I'm not an expert. So going to the superfluid helium-3, what is the mechanism for the pairing? Because you don't have phonons, is it just some?
Yeah. So the beautiful, indeed, I haven't mentioned it. Beautiful thing about helium-3 is that we don't have to argue about phonons. There are no phonons. Yeah.
Still argue.
Right. So it's believed it's a similar mechanism to this. This is one of the Yeah.
There's just correlation somehow between the.
There are strong interactions, short-range interactions between helium atoms. There are no Coulomb interactions, but there's hardcore interactions. And also van der Waals interaction,
They're spin dependent.
Yeah, so right, so it can definitely lead to this. Actually, that is being instability, being superconducting instability. We get this mechanism.
So far as I remember, the pi 3 of SO3 is set. Right?
Yeah.
Does it lead to any positive topological?
Does does. I don't know in the context of superconductivity, but these.
The question? Yeah.
So pi 3 of SO3 is the. Yeah. So I mean, we discussed the statistical mechanics of condensed matter systems. These logical defects tend to play an important role. For example.
You guys are discussing color superconductivity, right? Which is even a higher group. Anybody else? Yes, Professor.
Pi3 of S3 is relevant for helium-3 in 3 dimensions, but you have all these non-singular topological configurations, like Hoffman.
Right. This is not really a defect. It's pi 3.
You have P plus IP in one valley and P minus IP in the opposite valley. Is that correct?
No, it's P plus IP in both. Yeah. The orbital angular momentum of this state is 1.
So the symmetry with respect to the center of the Brillouin zone is also.
So that actually depends on whether the spin is singlet or triplet. So that's yeah. You can do a threefold rotation that preserves the value. So relative to under threefold rotation, it looks like spin 1. It's a system with a triangular symmetry. So E wave and P wave are actually the same presentation. The only distinction here is the spin. So relative to the center of the valley, it would look either like D wave or a P wave, depending on whether the spin. Yeah, center of the.
So, you have this, you said the order parameter is this SO3, but only part of it is gauged. I mean, so you have like a U1 part that's gauged. And is there any interesting consequence to the fact that part of the symmetry is gauged and part is slow?
There is. Let's discuss that offline, but there is. Yeah.
Are there experimental indications of things you mentioned, like the Josephson effect?
Yeah. Not of this phenomenon. These do form Josephson junctions. Again, not in the trilayer. In bilayer graphene, they do form Josephson junctions. But it's a Josephson junction between this superconductor and itself. It's same symmetry of the order parameter. There should actually be nothing very special. This AC thing has not been done before.
Andre?
Do you know in theory why one phase is spin triplet and another spin singlet?
Right. So in terms of the strongest interactions in the problem, which are the Coulomb interactions, which are maximum at small q, 2 phases should be exactly degenerate. Okay. So their balance is always subtle. And it turns out that if you just run this mechanism and include the large momentum transfer scattering, which is much weaker, that actually chooses in singlet for SC1. Now, in SC2, the normal state is a ferromagnet. It has to be spin triplet.
So, you said to get a triplet, you needed a nearby ferromagnetic state.
It helps.
Now, in this case, the ferromagnetism has this orbital character.
Yes.
Is that important? Like it could have been just the spin line.
That's right. So it's not just the spins; it's spin valley always involved in these kind of systems.
Could you clarify what this is?
So the thing is that in these systems, you have not just the spin of the electrons, you also have the valley, which is an orbital degree of freedom. And in this system, you can have spin ferromagnets, you can have orbital ferromagnets, which mean valley ferromagnets, or you can have both. And
My question was, how is the orbital ferromagnet playing a role in getting this speed? Is
Yeah.
it or is it not?
yeah, so I think it's not clear. The question is whether the nearby ferromagnetism is actually playing any role in superconductivity other than just competing with superconductivity. Clearly, when you go deep into the ferromagnetism, it kills the superconductor. This is the calculation I've actually done with Zalatel's group. Okay, we considered what we believe is the nearby generalized ferromagnet and looked at fluctuations of that. And it turns out it leads to exactly the same state, to our surprise.
So you're saying if it was a thin ferromagnet, it wouldn't give you that?
Not this, no.
So do you have a zero mode in the, okay, the vortex? I don't want to call it.
No. So yeah, right. So the question is, we know that superconductors of this type that break time-crystal symmetry often are what we call topological superconductors. Okay, these have interesting zero modes. This unfortunately is not a topological superconductor. Okay. The reason is precisely because of the fact that you have this hole pocket and electron pocket, they cancel each other.
Do you understand that resistivity that you showed?
Yeah. At the following level. So I would say this is the mechanism, and if for some reason electron phonon coupling is weak, then these are very, very low, clean and low density systems. So even if electron scattering is very strong, it won't show up in the resistivity. There's no umplap scattering.
But your resistivity was more or less flat in temperature.
That's exactly what you would expect. Yeah.
You expect flat resistance,
yes.
But that only usually comes from impurity. And you said there are no impurities.
Yeah, so that would the resistance might just come from the boundary system.
From the boundary. That we really don't. I think this is a very good example of the type of colloquium that should be given, which was, I think, quite comprehensible to people in other fields. I congratulate you.
Yeah.